and thermo and equilibrium. So the first thing we're going to talk about is kinetics and its relationship to, that says equilibrium, but that should say to thermo. So we saw this graph last unit, and we're seeing it again. We have 3 different cases here. And so let's just look at these and decide what's going on here and see how this is related to K. So the first case, case 1, what type of reaction is it? Exothermic, which means our delta H is negative, which means that heat is leaving, energy is going out. And now we want to find out, what is the magnitude of K? Is K going to be greater than 1, equal to 1, less than 1? Well, looking at this hill, which hill do you want to run up? If you have to run up these hills, which hill are you going to want to run up? The first one. So we're wanting to go this way, right? So that means it is what? How is it favored? The reactants are, or the products are favored. So it's a forward, it favors the forward reaction. Which means if I have products over reactant, we're going to favor the products. Which means, what can we say about the magnitude of K? It's greater than 1. The next one is an endothermic, which means that our delta H is positive, which means we put heat in. And what can we say about these hills? Which hill do you want to run up? You want to go up this big hill, or you want to go up this big hill? The second one, we're going to go this way. So we favor the reverse. So that means if I have products over reactants, then the reactants has more there. So what can we say about the magnitude of K here? K is less than 1. Here, what we're seeing in case 3 is a delta H of 0. So we have no heat loss or exchanged here. So what can we say about K here? K is equal to 1. These are all at equilibrium, okay? It just depends on which way you're being favored. So I would, hint, know how to do these, know what magnitude, which one's favored, all that. If you don't like my interpretation of it, there's some right there telling you how to interpret it. Now here is what we're going to look at is kinetics and equilibrium, the relationship to them two. So here is a mechanism. 3 mechanisms. We learned in the last unit which one is going to determine our rate law. The slow one. So let's go ahead and let's write our rate law based on the slow one.
Check the next page. The next page is examples. And then the next 3 pages after that are well.
Go grab one of those. I think there's extra ones over there underneath the poster. So rate is going to be equal to what? K, little k, times the concentration of C to the power of 1. Is everybody good with that?
So we're still not looking at order, right?
We're not looking at order, no. All right. What can you say? Look at the mechanism that came before our slowest mechanism. What do we see going on there? We have equilibrium. So this is a very fast, and we have equilibrium going on there. So that means that the proportionality of our C and the AB, they're kind of equal, okay? So we can do a substitution in here. Why can I not use the rate law we just used? We have to use the slowest, but why can I not use this? I cannot use this one at all. Right? Look at your overall equation at the end. What do we have at the end? What's our equation at the end? A plus B gives me what? E. I'm looking at all the mechanisms at the top. Why cannot
C's not even in the equation.
C's not in the equation? What do we call C? If it's an intermediate. Intermediates cannot be in your rate law. But since it's an equilibrium that is prior to it that makes that C, we can use that proportionality. So what we're going to do is now we're going to write our equilibrium expression for the equilibrium mechanism. So Kc is equal to, and this is big K this time, C over concentration of A times the concentration of B. I want to get C out of that, out of this rate law right up here. I want to get C out of there. How can I get what we just wrote? How can I use that to get that C out of there? Okay, so the concentration of C is equal to
K times concentration of A concentration of B.
C is equal to the equilibrium constant times the concentration of A times the concentration of B. So now what I want to do is I want to take this, what C is equal to, and I'm going to substitute it in right there for C. So I'm going to rewrite my rate law, and my rate law with that substitution. So rate is equal to K, little k, times big K, times the concentration of A, times the concentration of B. Little k is a constant, big K is a constant. A constant times a constant, so what? A constant times a constant equals a constant. It's a constant. So those two K's, I don't like looking at those two K's, so I'm going to rewrite this and say that rate is equal to K, and I'm going to call this K prime, just so I know it's another one, A times B. If you don't want to use K prime and you just end up just putting that, I know that these two became one little K, that's good.
Hey, Miss White, I have a question.
Uh-huh.
Okay, do both of those K's have the same constant?
No, they're two different values. One's a rate law constant, and one's the rate law value, and one's the equilibrium constant.
So why do we get to do that?
Because they're two constants.
They'll always have the same value.
Well, if I multiply them together, yes.
That's how.
I am not ever going to ask you to solve for this. I will make you solve for the rate equals K, the expression, and substituting in for the expression. I'm not going to ask you, nor will the AP ask you, to solve for this. This is as far as I want you to go. Yes?
Does the K prime in no way has to do with derivatives?
No. It's just saying it's a different one. Okay?
Is that a big K prime or a little K prime?
I did little k since it's a rate law. Is that okay?
Sure.
Okay, so
Okay.
let's do one more. I have two more for y'all. And then we're done. Now here, we have these two here. Determine the rate law. So our rate law, and from now on, I expect you to use the slow step to determine the rate law. That's not going to be it anymore. You've got to look and see, is there a substitution rate law in there that I can use? Can I go off of equilibrium? All right, so determine the rate law. So first of all, rate is equal to our slow step, which is, rate is equal to K times NOBR2 times NO. We have a slow step, but prior to my slow step is that fast equilibrium, which means I can do a substitution. So first of all, let's see who we're substituting in there for. Who's going away? NO. Oh, no, NO stays. BR2 goes away. So I need to substitute in for NOBR2. So write your equilibrium expression based on your fast equilibrium. So Kc is equal to NOBR over the concentration of NO times the concentration of BR2. Oh, BR2, yes, sorry. We need to solve for NOBR2. So that means that Kc times NO times BR2. So we've got our substitution equation, and we're going to take that and we're going to plug it in up there. So when I plug it in, I end up with rate is equal to little k times big Kc times NO times BR2 times NO. How can we clean this up? Rate is equal to, I don't like those two K's, so I'm going to do K prime. NO squared BR2. Good? And lastly, let's do one where we have to take the square root of something.
Could you rewrite that as NO squared, or would that be wrong?
I did.
Oh, I'm sorry.
Okay, determine the rate law. So, again, start with your slow. So rate is equal to K times the concentration of Br times the concentration of H2. I see this equilibrium out here, and that tells me, oh, I better do a substitution. So let me see who I need to substitute for. So it looks like I am substituting for Br.
Just kidding.
So Kc is equal to Br, concentration of Br squared, over my reactants, which is Br2. And I have to get this solved so that I can substitute in for Br. So Kc times Br2 is equal to concentration of Br squared. Huh?
What about the H2?
It's not in the first equation.
It's not in the first, it's not in my equilibrium, fast equilibrium. So what do I do now? I can't just throw that in there because I don't have a Br squared. So I need to take the square root, or we're going to say Kc to the 1/2 power times BR2 to the 1/2 power is equal to BR. And now we can take this whole thing right here and substitute it in our rate law. So rate is equal to little k times big KC to the 1/2 times BR2 to the 1/2 times H2. And then clean it up further and say that rate is equal to K prime.
That half doesn't matter.
Nope, because that a square root of the K, it's still a constant. BR 1/2 times H2.
Would it be
BR2, yes.
So if we had left it with the square root instead of the 1/2, that'd be wrong.
That'll be all right. So that is substitution. I would know how to do this by next week. So your homework is over this stuff. So 4D.